Let's look at cycle time, and I think the first thing to keep in mind when we start talking about cycle time is to think in terms of process. We've already done a little bit of work with process flow and process mapping, or flow charting or value stream mapping, but to try to think of everything that goes on in your business and in your personal life as a process. And every process just means there's a certain set of steps that has to happen. There's a certain set of sequences that has to happen. You know, those steps, something has to come first, something has to come second. And when we start thinking about cycle time, it's to really then kind of get down to a little bit more detail of how long do each of those steps actually take to complete. And we have this term bottleneck. Probably a lot of you are familiar with the bottleneck. You know, physically the bottleneck is the part on the bottle that restricts the flow. So when we think about a process and we talk about the bottleneck in the process, it's whatever step in that process keeps the entire process from going any faster. And sometimes we find bottlenecks are physical restrictions. Sometimes bottlenecks have to do with the equipment and it's kind of how productive or how much capacity you have out of a single piece of equipment. Sometimes it's a person that is the bottleneck. But when we think about a process being a sequence of a set of steps, we need to think about where's the bottleneck in that process? What keeps it from going any faster than it's currently going? And a good way to find the bottleneck is you just look for inventory. And again, inventory can be parts, inventory can be work orders or jobs, inventory can be customers, it can be, you know, humans, people that are piled up. And wherever you have a bottleneck, what you're going to find is that you have inventory piled up in front of that bottleneck because it's restricting the flow of the work moving any faster. So that's one good way without getting real detailed and without doing a whole lot of analysis. When you look for the bottleneck, is you just look for where's all the inventory. And normally what you're going to find is that a bottleneck occurs because you have some finite or some limited amount of capacity, and that station or that step has less capacity or is utilizing less capacity than the other steps that are in the entire process. The next thing that you see sort of downstream from a bottleneck is what we in operations call starving. And all that means is that the people who are downstream of the bottleneck, who are waiting for the bottleneck operation to pass their work on to them or to move out of the way so that they can get in and do their work, they have nothing to do. And so we call that starving. They're sort of there, available and waiting. They have excess capacity, but there's nothing to do with that capacity. Blocking is just the opposite. Blocking is what happens upstream from the bottleneck, and typically what happens upstream, if the bottleneck has enough of a difference in capacity as the steps that happen preceding to it, you can't let inventory just pile up forever, whether it's customers, or whether it's products, or whether it's jobs. So what happens is those people who are doing the steps leading up to the bottleneck, they have to slow down. So they're being blocked. They can't move any more work forward because there's no room to move any more work forward. We see blocking in lots of different examples, and here's a little section of a warehouse, and when you have blocking in a warehouse, there's just physically no room to move the product in to begin the next processing step. And there's a concept in operations management called theory of constraints. That's what the TOC, management principles, theory of constraints. If any of you have read the book The Goal, the author that wrote the book The Goal, he's really the one who created theory of constraints, and he has some kind of basic guidelines. And one thing is to look at a process, identify the bottleneck, and identify the steps that are not the bottleneck, and determine how to treat each of those steps. So if you have steps that are not the bottleneck, what you want to do is move jobs as fast as possible up to the bottleneck. Idle time is acceptable, utilization may be low, which means at some point you have to stop pushing product or pushing jobs, and everyone sees that happen in the real world. You can only build up so many jobs up to a certain point, and then you have to slow down. Use small batches to keep work flowing to the bottleneck, and that's kind of this ideal of just-in-time, small batch sizes, or we talked about earlier about one-piece flow or continuous flow. It's moving small groups of work up there rather than large groups of work. What do they say about the bottleneck operation? Schedules first because these are critical, which means they get the schedule that most suits their requirements. So when you think about the sequence of jobs that need to be done, typically different workstations have a different sequence that makes it easiest for them. Well, the bottleneck, sort of the good news for the people at the bottleneck operation, is they get to choose the schedule. The schedule is designed so that it makes their work most efficient. To recognize this, that an hour lost at the bottleneck is an hour lost for the entire organization, because the speed of the bottleneck controls the speed of the entire organization. I think sometimes people sort of lose sight of that, and I think, well, an hour lost at the bottleneck operation is just an hour at that particular workstation or for that particular trade, but they're going to slow down the entire system. So really need to look at it like an hour lost there is an hour lost for the entire system, which means it's a very expensive hour that's lost. Use larger lot sizes and minimize setup time. So this is kind of the opposite of what we see in lean and just in time. This one's saying use a larger lot size, process more work at once. That's farther away from one piece flow or continuous flow, but you're doing that to try to minimize setup time. So anything we can do to maximize that time, anything we can do to minimize downtime is what we need to do at the bottleneck. We got to really focus at the bottleneck step and really figure out how do we speed that step up, even if it comes at the detriment of some of the non-bottleneck steps. So here's our steps for a theory of constraint. Identify the constraint or the bottleneck. Where does the work pile up? So that's the first thing, is you got to recognize where in your process is a bottleneck occurring, or sort of what step is it. Increase utilization efficiency at that constraint. So we're going to do anything we can to make the efficiency and the productivity and the utilization of that constraint step or constraint person or constraint machine. We're going to do everything we can to make it as productive as it can be. Set up all processes to serve the constraint. Do what's best for the constraint operation, even if it makes the non-constraint operation less efficient. So again, what that means is you may have steps or you may have people that want work done a certain way, but if they're not the bottleneck, we have to be a slave to the bottleneck. We have to do anything we can to make that bottleneck step faster and more efficient. If you have to increase the capacity of the constraint with additional resources, that's always sort of an action of last choice. But if you really say, I'm getting everything I can get out of this work group, or I'm getting everything I can get out of this machine, if the bottleneck is moving as fast as it can move, and there's no more capacity and there's no more productivity to be gained, then you may have to double up on the capacity. So you may have to have a second machine or a second crew at that bottleneck operation. In a manufacturing environment, you see that a lot with like a second shift or a third shift, and maybe you don't run every single machine on that second or third shift. Maybe you run like we call a skeleton crew, just a small crew, and all we do in that situation is put that crew at the bottleneck workstations. And then once you've increased the capacity of that bottleneck, you just sort of go back to step one, because there's always going to be a new constraint or a new bottleneck. We've seen this slide before, just want to touch base on it again. We think about cycle time. We have some terminology and some factors or variables we need to think about. One is the work in process, and those of you who are in a manufacturing environment are probably very familiar with using the term work in process. Another thing is the exit rate. And the exit rate is the speed that we're finishing products or finishing jobs, that output rate. So when we think about cycle time, how long does it take from the time we start a new job at the beginning of the process until that job sort of comes out the other end finished? We have a ratio that we're going to be able to work with. And the ratio is what's known as Little's Law, and it just says cycle time is a ratio of the work in process divided by the exit rate. And obviously in a lean environment, our goal is to decrease the cycle time. We want to make the time that it takes from starting the job to finishing the job as small as possible. And so if you think back to, I don't know, 6th grade math or something like that, and you think, if I want this number to go down, if I want cycle time to go down, then I either have to make this number WIP go down, or have to make this number exit rate go up. Sometimes you can't increase the exit rate. You know, some processes have a certain amount of time and you can only process at that speed. You think about maybe something that goes into an oven and it has to cook for a certain amount of time. Well, you can't speed that exit rate up. What you can and what you do have control over is this WIP. It's the amount of work that's in your system. It's the amount of jobs or projects or products that you start in the system. And if you can reduce that WIP, then you reduce the cycle time. Here's an example of that, just thinking about lines at Disneyland in March. We think about what's the WIP. So, here's a waiting line, and here's the exits here. Our WIP is 1, 2, 3, 4, 5. So we've got 5 people in line. And if the exit rate is 1 person every minute, then the cycle time, somebody that walks up here and gets in the back of the line is going to be the WIP, 5 people divided by the exit rate of 1. So it's going to be 5 minutes before that last person sort of gets up to be served. Now think about that same situation in July. The exit rate doesn't change. The exit rate is still 1 person per minute. So we think about this being like a ride. The ride doesn't go any faster in July than it goes in March. It doesn't go any slower than it goes in March. It still processes 1 person per minute. But if you have 1 extra person come up and get in line, but now there's 13 people in line, then the WIP is 13. So their cycle time is going to be 13 minutes before they're processed. So let's see what this does. We think about our current process that maybe has a lot of WIP in it. Would have a long cycle time because WIP is high. Would have a low flexibility because if I decide to make a change, I basically have to clear out everything that's in the system before that change can be implemented. And what Lean focuses on is trying to reduce that amount of WIP, so that makes our cycle time go down. We know that from Little's Law. And it also makes our flexibility go up because we're able to respond quicker. So this new process with less amount of WIP gives us a short cycle time. One thing that does for us is it gives us faster feedback. So, I start a job here in the current process, and if I have a long cycle time, I don't know how that job sort of turns out until the end, until a long cycle time. When I have a short cycle time and I start a job, I see how the end turns out very quickly. So I get faster feedback. I would actually reduce the risk for changes because if I have less projects or less product that's already been started, then when there is a change in requirements, I have less material, less jobs that have already been started that are going to have to try to make a change in midstream. Improve customer satisfaction because I do have more flexibility and a shorter cycle time, so I'm more responsive with this kind of arrangement. So let's look at a nightmare here. This looks like a nightmare, right? One of these football stadiums with people jam-packed. We're going to consider the stadium filled with spectators that must leave through 1 exit. So there's only 1 turnstile in this, looks like University of Michigan football stadium. So everybody's got to go out 1 exit. The exit has a turnstile, and people are able to cross the turnstile rate of 20 people per minute. That sounds like an exit rate or a throughput rate there when I see 20 people per minute. And the first question is, if there are 20,000 people in the crowd, that looks like a whole lot more than 20,000 people. But if there are 20,000 people in the crowd, what's the throughput rate? And the throughput rate doesn't change. The throughput rate is 20 people per minute. The next question says, if there's 40,000 people in the crowd, what's the throughput rate? And that doesn't change. It's still 20 people per minute. The turnstile only turns so fast. And just because there's more people piled up behind it doesn't mean that the turnstile is going to turn any faster. You can only push so much through the system as so fast, and more people piled up doesn't make that go any faster. Here's my little man, Speed Racer. Hey, Speed Racer. Let's look at a question here. If there's 20,000 people in this crowd and 1 extra person is added, how long does it take to get that person out of the stadium? So we just use our Little's Law equation. Cycle time equals WIP over exits. The WIP is 20,000. The exit rate is 20 people per minute. And so I take my 20,000 people in the stadium, divide by 20 people per minute, and it tells me 1,000 minutes. So that person that walks up at the back of a 20,000 person stadium is going to take them 1,000 minutes to get out. Same situation here, but we got 40,000 people. 1 person walks up to the back of the line. Still, cycle time is WIP over exits or WIP over throughput rate. The WIP is 40,000 now. My exit or throughput rate is still 20 people per minute, and now it takes 200 minutes to get out. So again, this is kind of like the Disneyland example. The throughput rate doesn't go up or down, but when WIP goes up, then your cycle time goes up. And I do quite a bit of work in consulting, and this is one of the things that I sort of look for. You don't find this in most of the academic literature, but when I walk around and I look at jobs and I just try to get a feel for, are there cycle time issues? One of the things I notice, if there's paperwork that basically ride with a job, and I see stickers on it like this job is hot, or this job is hot, or this job is super hot, or some kind of ASAP, what that tells me is that you have a cycle time that on average is too long. So you got too much WIP in your system. If you just put a job in at the beginning of the system and let it flow through naturally, it's going to take too long. So what you do is you expedite specific orders to meet customer requirements. But when you expedite those specific orders, what you're doing is taking other orders and pushing them to the back of the line. So your average cycle time doesn't change. It's just that you show that, hey, we can take one product or one job and we can speed it through the system, but then all the other jobs get slowed down. And that is absolutely a sure sign that you have cycle time problems. Again, you can think of cycle time in terms of, it has to do with inventory, and that inventory can be products, that inventory can be people or customers, that inventory can just be papers. If you're in an administrative position, you're on a desk, it may be just papers or emails. It may be projects. And again, this Little's Law tells us that cycle time is a ratio of the WIP divided by the exit rate. So it's directly proportional to the amount of work in process, the amount of stuff that you've started. So here's a simple process that we saw in the very beginning. This looks like some kind of sales process, I guess. We're going to greet a customer. We're going to take their order. We're going to pull their order. We're going to check them out. 1 minute to greet customers, a minute to take an order, 2 minutes to pull the order, 1 minute to check out. What's a constraint in the system? Clearly, this is our bottleneck. This is our constraint, pulling an order. It takes 2 minutes. What's the throughput rate of this system? And sometimes it's a little bit of a tricky question, maybe. You say, what's the throughput rate? In other words, how fast do customers sort of exit out this system? Well, you might say, well, I guess it's 1 a minute, 1 customer per minute. But think about this. If we let the system run for a while, and this step is running at 1 a minute, what happens here? The pull and order can't feed a person or an order at 1 a minute. So everybody in this entire process is going to have to slow down to 2 minutes. So 1 order every 2 minutes is going to be our throughput rate. What's the effective decrease in time required to check out? So, and you see this a lot in large companies. People kind of live in a little micro environment. They do what's best for their individual department. They do what's best for their individual team. People are here on the checkout team and they say, what are you going to do this year to make improvements? And they say, oh, we're going to speed up the checkout time and it's going to save us money. And you think about this system as a whole and you say, what happens if you decrease the time to checkout? And the answer is nothing from the system as a whole. This is still your bottleneck, pulling the order. So checking out any faster doesn't really do anything for us. So what should we do if our goal is to increase throughput of the system? We have to decrease the time that it takes to pull an order. And of course, the first thing that we ought to do is look at, well, what's the process for pulling an order? Is there anything we can do to make that process go faster? When we give people like a paper, a pick list or a pull list that they're pulling from, is it in the most efficient way possible? The people who are pulling an order, is the warehouse or wherever the material that they're pulling from, is it arranged efficiently? Have the people been trained? Do they have the right kind of equipment to pull the order? And if all those answers are yes, if all the answers are this is absolutely as fast as we can pull an order. It takes 2 minutes to pull an order, and it cannot be sped up. And I would probably question that if I were sitting there in the real world and I saw that. But let's say that's as fast as you can pull an order. Then your only alternative becomes somehow kind of duplicating that workstation. And so I might take that workstation and split it in two, and in a sense it's almost like having a 1 minute and a 1 minute processing time. And so now I can do 60 an hour out of step 1, I can do 60 an hour out of step 2. I can do 30 an hour out of step, maybe we'll call that 3A, but I can do 30 an hour out of step 3B. And so what I really end up with is 60 an hour, and then I can do 60 an hour out of the fourth step. So now my throughput becomes 60 an hour rather than 30 an hour.